Hi, our names are Jack and Kushal, and our project is Diffusion Policy. Is scaling all you need? As we know, robots can learn manipulation skills from demonstrations using diffusion policies. However, learned policies often fail under small distribution shifts. Because of this, the two main questions we ask in our project are: how well do diffusion policies generalize to out-of-distribution tasks? And how does performance scale with the amount of training data? In our approach, we train diffusion policy using a conditional 1D unit architecture and the standard DDPM laws. More precisely, we take ground truth actions from expert demonstrations, add noise to them, and train the model to do noisy actions. So at inference time, the model goes from noise to actions, generating its own trajectories. We evaluate the model in two generalization settings. First, generalization to new positions, and second, to the presence of new obstacles. In both settings, the protocol is the same. We start by training a baseline model on 200 demonstrations, measure its out-of-distribution performance, and then gradually add more out-of-distribution demonstrations and retrain. We perform our experiments on the money skip simulator, and we create the expert demonstrations using handcrafted motion planners. We begin with generalization to new positions. Here, the model is trained on 200 demonstrations in region A, and we test its performance in region B, which is unseen during training. Our baseline model achieves around 95% success in region A, as shown in the left video. But in region B, its success rate drops below 4%. In the right video, we see that it doesn't even manage to grasp the cube. To address this, we add between 1 and 30 demonstrations from region B to the training data. As shown in the red curve, performance increases almost linearly as more demonstrations are added. Notably, with only 30 new demonstrations from region B, it reaches over 94% generalization success. In the video, we can also observe that the robot successfully completes the task in region B.
Furthermore, we evaluate the robot in other regions of the table, such as region C, which is unseen during training. Even without any demonstrations from that region, performance improves as we add more region B demonstrations, suggesting some degree of interpolation capability. Next, we look at generalization to the presence of an obstacle. In this case, the baseline model achieves 0% success. It either fails to grasp the cube or collides with the obstacle. Again, we add more demonstrations, this time including the obstacle. To create these demonstrations, we design a motion planner that takes a detour around it. As before, performance increases quickly as we add demonstrations. Notably, with only 40 demonstrations, the robot reaches 81% success. Even more interestingly, the robot learns to combine both modes of behavior. In the videos, we see that when there is no obstacle, it takes a straight path, and when there is an obstacle, it performs a detour. The robot even shows new behaviors not present in the training data. For instance, it produces 2-segment or 4-segment detours, even though all demonstrations use 3-segment detours. To summarize, we have shown that adding only about 10 to 15% of targeted demonstrations can yield large generalization gains, raising success rates from under 5 to over 70%. We also observe that diffusion policies enable multimodal behavior, letting the robot succeed in both out-of-distribution and in-distribution tasks. Furthermore, the models exhibit new capabilities, such as interpolating between regions or generating trajectories unseen during training. However, for harder tasks such as those involving obstacles, achieving high accuracy requires more demonstrations. This suggests that data efficiency depends on task complexity. To better understand this, future work could explore more complex, longer horizon tasks and study generalization with vision-based observations and real-world experiments. Thank you.